something you have not ever been able to do before. We've never been able to integrate a natural log. We could do the derivative of a natural log, but you could never integrate a natural log. Back when we were doing normal integration, I told you if you saw a natural log in a problem, you knew you had to use substitute it because we didn't know how to integrate it. Well, thanks to integration by parts, now we can. Okay, but if you looked at that problem, would you say that's an integration by parts problem? Does it have two different things being multiplied?
Nope.
I mean, the other one was clearly two separate functions getting multiplied. It screamed at you.
You make dx the one that you're going to integrate?
Yes, you do. In this case, it doesn't look like it because it's just one term. But yeah, you still do integration by parts. So you have to make one of them u, one of them dv. Well, okay, which one do you want to do the derivative of? We know how to do derivative of natural log of x. And so therefore, it's just the lonely dx has to be the dv part. So what's du going to be? 1 over x. But now I'm going to integrate, so dv becomes v, so yeah, dx becomes x. It's technically like you have a 1, I'm sitting in front of them, you're integrating a 1, it's 1 dv and 1 dx. Ah, thank you, yes, we do need the dx. Okay, do I need to rewrite the whole formula up there for you?
Yes.
Yes? Okay. So if you have v du, it equals the integration of u times v. No, not v du. I did that right. I'm doing this way because I only ever learned this side. I never learned the other side.
Yeah. You should just ignore the left side.
Yeah. I just know I start out with a u and a dv on the left side. So, okay. So now, but I also see it as a pattern. The formula u times v. I know I have to go diagonally minus the integration of the bottom two. You do u times v, which would be diagonally, minus the integration of the bottom two.
The top right's completely irrelevant.
Yeah, the top right you're actually not using. But you couldn't have got the bottom right if you didn't start with the top right.
Got me.
Okay. So, in this case, what's u times v? So, and they'll put the x in front. They'll write it as x times natural log of x minus the integration of,
X times 1 over x.
yeah, v is x times 1 over x. So it actually turns out pretty sweet. Yeah, it's just 1.
Integration of 1.
Oh, golly gee, can we do the integration of 1?
Can we not?
Yes. Yeah, we asked that like, that seemed like it couldn't just be possible. And to that, you just discovered the integration rule for natural log. It's actually one, particularly anybody looking at future calculus, I'd stick that one in my head. The integration of natural log is x natural log of x. I should have an absolute value on that, sorry.
Look on our journal.
Minus x plus c. Yes, I'm sure it is on your journal to write that rule out somewhere. That is a rule.
Oh, I gotta do the integration by parts too. Where is it, you know?
Okay, so while you're filling in formulas on your journal, then yes, you did just discover the integration of tangent is equal to a negative natural log of cosine x. Plus c. We just discovered in working this problem that the integration of tangent turns out to be, it actually was a negative natural log because we changed that sign up there. So if you ever don't want to have to go through the whole u substitution to integrate tangent, you can just learn that it's negative natural log of cosine.
So if we just memorize it, we can just like write down answers.
Yeah, you just fill it in, yeah. So you don't have to work it all out every time, yeah. If you're willing to learn it. Now, and depending on who you may get, if you're taking Calc 2, who you may get as a college professor, I was expected to know all those. I actually had this little side notebook, small notebook I carried around with me. Had all my formulas in it, and I'd run them all before a test, make sure I still had them all.
Little Bible for math.
Kind of, sort of, yeah.
This is my math Bible.
Okay. This problem
Yeah, I don't think they
has
have
more pizzazz to it. The question would be why?
Because it wants to be fabulous.
Well, if you use the 2x, I mean, it doesn't look like that's different. It's got two parts. Big deal.
You can use substitute. You can't.
So the question here is, this is a little trickier. Both of those can do a derivative. Both of those can integrate fairly easily. So how do you know which one should be which?
Let's do U as E. Just because you're being
Okay, so are you all, he wanted to do U as E to 2x. We buying that or not?
yeah. If we're wrong, we're just gonna redo it. I like derivative.
Okay, if we're doing that to e to the 2x, and we're doing dv is x squared.
Or we can make it dx and do U could be x squared times U.
So what's going to happen, our derivative of U, no big deal, other than you would have to remember to do what?
Multiply the 2x.
Derivative of E is itself, but then you have to chain rule it and times by 2, which they would throw the 2 in front rather than in back. Okay. Yeah, times dx. But what's going to happen over here on V?
X to the third over 3.
It's going to go
X to the 4.
you're going to add 1 to the power, divide by the power, so it's just going to be x cubed over 3.
Read it the other way.
So, okay, it doesn't look, when you do U times V, that doesn't look too bad. It doesn't matter what those two are. But look at what you're going to get when you go to integrate this.
How about now? Let's do the
Okay.
other way. I like.
Okay, because every time you integrate this,
Like she was trying to mess with us.
every time you integrate that, do I get to talk?
Yeah.
Every time you integrate this, it's going to keep, the power in x is going to keep getting higher and higher and higher and higher. You know, e to the 2x is, anytime you do a derivative or an integration, it's going to stay on e to the 2x. So you're just going to keep getting two multiplied things together. We need that power on x to go down so that when we do the derivative, we eventually get rid of that term. Okay, so yes, we were backwards here. We should have done it the other way. So we would want u to be x squared and e to the 2x to be, and thank you, e to the 2x to be x. Okay. So when I do du, that's no problem. That's just 2x dx. We like that. Okay, now, I think I showed some of you this once during seminar, but there's a fast and easy way to integrate an e to the 2x. We probably once need to do it slow, but then you'll save yourself a lot of time and trouble. But right now, are you allowed to integrate an e to the 2x? You would technically have to use substitute it, because it has to be e to a single variable. But if I did use substitute it, what would I get when I do the derivative of it? I just get a 2, which then divides over to the other side and becomes du over 2. So when I integrate it, that's just a 1/2 we can put out front, e to the u, and then of course if I put my 2x back in there, I have 1/2 e to the 2x. Okay, so now, tell me how you could have gotten that answer without doing all that work. Yeah, if it's 2 to the x, the integration is going to be 1/2 e to the 2x. Okay, that you have to use, that's a whole other world. This is just if it's 3x, 4x, 10x, if there's just a number times x, it's going to be that particular rule. So yes, this is on your journal somewhere, right, the integration rules. It says, I believe I have e to the nx, probably. So what's the rule going to be?
So 1 over n times e.
Yeah, 1 over n times e to the nx.
Could you just do e to the nx over here?
You could use nx over n if you like it that way. I always pull the number out front, so I want it out of my way. And the same thing then goes, well, we're talking about, we might as well talk about the whole ball of wax. If you're integrating, say, a sine of 4x, once again, just has to be an x, not x squared, not x cubed. Same thing happens. If you do your u substitution on that 4x, you're going to end up with a 1/4. So yes, the integration of sine of 4x, I should put a dx on that. or actually let me make it sine of nx, is just simply 1 over n times, what is the integration of sine? Integration of sine x is, we're missing something. Negative. It's a co. It came out a co, you put a negative on it. Did I ask you for cosine on there as well or not?
Yes. Cotangent.
Ah, cotangent. Okay. Well, we'll see if you can tell me cotangent here. Cotangent is just like tangent. I should have done that back on the tangent page, actually.
Sine this time?
This time, yeah, you have to change it to cosine over sine. So if I was going to integrate it the same way I did that tangent back there, and I substitute out the sine, can you tell me what I'm going to get? Natural log of sine, because you're going to substitute the bottom. Will it be positive or negative? It'll be positive because the derivative of sine will be a positive cosine. So you'll get natural log of sine of x plus c. So that's the...
Memorize.
For where you're headed mathematically, yes, I'd memorize them. You're going to use them over and over.
In my career, or just for my education?
Well, having not done your career, I doubt, it kind of probably depends on what area, what kind of a business you end up working for in the end.
Yeah. I was going to do horse races, doing lines on horse races, work with the mafia.
Great, Alex, yes, that's what I always want to say. Yes, one of my students works for the mafia, yes.
I'm a very smart mafia member.
Okay.
And the mafia is smart enough to hire an actuary to figure out their races. They're pretty smart. They're going to make it. They're going to win.
All right, so now, tell me what V is going to be now that we've learned these shortcuts. 1/2 e to the 2x, and we're not going to bother to write the plus c on there. Okay, those little rules, by the way, are not only going to show up here on integration by parts, they're going to show up on several other things throughout this chapter that you'll want those shortcuts. Okay, so now, do integration by parts. What's my rule? UV, which I'm going to throw the 1/2 in front, 1/2 x squared e to the 2x, minus the integration of v du. Okay, so when I multiply those bottom two pieces together, do we agree the 2's are going to cancel? 2 times 1/2, so I'm really going to end up with this x times e to the 2x. All right, so now what? Can I use substitute and get this to integrate now?
Yeah, u is 2x.
But will the derivative give me an x to cancel that x?
Oh, no, maybe.
No.
Do you do it again?
Yes, it's called repeated, sorry. It's called repeated integration by parts. Sometimes you have to do it twice. Sometimes you have to do it 3 times.
All right.
That's the worst I've ever seen, but yes. But now, do it exactly the same as you did the first time.
So when you end up with the integration of the same function you started with, and then you're
Because if you reverse it, like here we made our x be u. If you flip it back the other way, you'll just end up back where you started. So continue. We had u being x squared, so now we have u being x. Follow the same pattern you did on your first. dv is still e to the 2x. You have to keep in the same pattern, or you'll just put yourself in an infinite loop. So now, though, the derivative, du equals dx, and when I integrate this one, it's the same thing we just did. It's 1/2 e to the 2x. Okay, and then there's a tiny little algebra thing you have to watch out for that you don't mess up. This front part's still sitting here. But then we had this minus. So I'm going to write that minus, and I'm going to write a bracket here for a moment. Because now, when I do integration by parts again, I have to do u times v It's going to change, yeah, here in a second. So that's going to be u times v that multiply the diagonal, 1/2 x e to the 2x, minus the integration of
dx, 1/2 e to 2x.
v du, the bottom piece, which is, yes, just a, that one shouldn't have a dx on it. I got dx happy. 1/2 e to the 2x dx. Okay.
Bracket.
I reckon, yeah, technically close your bracket. I personally then always distribute my negative right now, or I have a tendency to forget to, but that negative, that first negative we had up front, needs to distribute in there. So if it was me, I would go make this minus 1/2, make that integration a positive, so that way I know I've dealt with the negative. Okay. Now, is this last little integration anything fancy?
Would be 1/4 e to the 2x.
Yeah. It's just a plain e to the 2x. We can do that one now. We have our shortcut rule for it. So these first two pieces just sit out here. And we know the integration of e to the 2x.
So it'd be 1/4, right?
Yeah, so it's going to become 1/4 because you're going to have another 1/2. So it's going to become 1/4 e to the 2x plus c, and you have successfully completed your problem. How awesome was that?
That gives you the area under that curve. When are you going to see that in a function? That helps you understand.
You wouldn't necessarily, exponential functions are more for the reasons we use exponential functions, growth, decay, how much stuff come down, and Alex, if you're going into the land of probability with an actuary, guess how they really estimate the area and each of those, that chart I gave you to look up values on a normal curve, guess how they really get it?
They look at it.
They get a formula for the curve, and they find area using calculus. You're headed to probability, and normal curves have all that with calculus-based stuff.
It's like a blast. Anyway.
So
Well,
that's.
future first world watch.
Oh, thank you.
And once I figure